Hello, and thank you for joining me for today's lesson on Newton's second law. In the last video, we talked about Newton's first law, that an object in motion will stay in motion, object at rest will stay at rest unless acted on by an outside force. So when this happens, when we have an outside force acting on it, our objects are going to move. And those are called unbalanced forces. But when an object moves, it's going to have an acceleration. And so Newton's second law explains how an object will accelerate depending on its mass and the force. So his second law states that the acceleration of an object is directly proportional to the net force on the object and inversely proportional to the object's mass. So these two terms, directly proportional and inversely proportional, are very important for understanding this law. So we talk directly proportional. This means that with acceleration and force, if acceleration goes up, so does the force. Or if the force goes up, so does the acceleration. If the force goes down, the acceleration also goes down. The object accelerates at a slower rate. On the flip side, if we're talking acceleration and mass, I have mass and acceleration. If my mass goes up, I increase the mass of an object, it's going to accelerate less given the force. Or if I increase the acceleration on an object, it would have to have less mass. So one of the ways that I think about this, and this one, is I always ask people, do you know who this lady is? Do you know who your ma is? And kids will say, yeah, I know who ma is. Okay, have you ever disagreed with your ma before? And they say yes, and I say, and what happens? And they said, well, she didn't get very happy with me. I said, you're right. And why did you disagree? Well, because I thought this was a good idea. This was my idea. And my ma thought this was a really bad idea. And so one went up and the other went down. That's inversely proportional. One increases, the other decreases. And this is how we're going to look at this. And when we look at this, we can set it up into this relationship. So if F and A both work in terms of one goes up, the other goes up, they can be on opposite sides of the equal sign. So 2 increases to 4, this 2 also has to increase to 4. Now, because mass and acceleration are inversely proportional, they have to end up on the same side. So these two are multiplied, that if mass goes up, acceleration has to go down in order to equal the same force. For example, if I have a force of 100 newtons, and I start with a mass of, we'll go 10 kilograms. In order to get my acceleration, I would have to divide 10 across, and I would come to 100 divided by 10 gives me A equals 10 meters per second squared. Okay, now I keep the force the same. I still have 100 Newton force if I cut my mass in half. So now I'm exerting 100 Newton force on a 5 kilogram object. Now if I divide my 5 kilograms across, 100 divided by 5, A is going to equal 20 meters per second squared. You will notice, in this case, I cut my mass in half. I divided it by 2, which meant that my acceleration had to double or be multiplied by 2 in order to get the same force. This is Newton's second law, that's what we're going to practice with. So to do this, if you think about it, equal forces, if you have equal forces, a larger mass is going to accelerate less than a smaller mass. So to push with 50 newtons on a big box versus a small box, the big box is going to move less. And that's just kind of the reality check for this. I can see this, I can put this into action, I can conceptualize this idea. Okay, so then we add numbers to it. When we do numbers, we have this equation, which you need to write down and make sure you have. Force equals mass times acceleration. For this equation, mass always has to be measured in kilograms, and acceleration always has to be in meters per second squared. When we do this, we get units of either you can write this out, kilogram meters per second squared, or they've named the unit for force after the guy that did a whole bunch of work with it. They named it, let's call this a Newton. So 1 Newton is equal to 1 kilogram times 1 meter per second squared, which is the same as roughly 2.25 or 0.225 pounds, or 1 pound is the same as about 4.45 newtons. I don't ask you to know those conversions. I don't know those conversions right offhand, but this calculation is going to be really important. You have to be able to use that here coming up. So we're going to practice because that's how we learn. So for starters, you have zookeepers lift a stretcher that holds a sedated lion. The total mass of the lion and the stretcher is 175 kilograms. The upward acceleration of the lion in the stretcher is 0.657 meters per second squared. I want to know what force is needed to produce the acceleration of the lion in the stretcher. So things that I know, or things that I need to know. And we should have a picture. In this case, I'm just going to draw a stretcher with a box on it. And I'm going to label this as 175 kilograms. And I lift it up with an acceleration of 0.657 meters per second squared. So I'm going to fill in my blanks over here. I know 0.657 meters per second squared, and I know the mass is 175 kilograms. I'm looking for force. So my equation for force, remember, is F equals M times A. So if I take 175 kilograms and I take it times 0.0657, I get an answer of, so F equals 175 kilograms times 0.657 meters per second squared. F equals 115, and I can do either kilograms times meters per second squared, or I can have 115 newtons. Now, since this has an acceleration with it, acceleration is a vector quantity, meaning it has both mass or magnitude and direction. We talked force has both a magnitude and a direction. So in this case, I need a direction of up. So in both of those, I need a direction of up to make sure we know that's the direction the force is going. Okay, I'm going to give you some practice ones to try on your own. And then, actually, I'm going to work through, I'll give you some practice ones to try on your own. So here's a couple questions. So one, I want to know what is the net force needed to accelerate a 1.6 times 10 to the third kilograms automobile forward at a rate of 2 meters per second squared. So you can work through that question. When you get that done, number two tells you that a baseball accelerates downward at 9.8 meters per second squared. If the gravitational force is the only force acting on the baseball and is 1.4 newtons, what is the baseball's mass? So in this question, you're going to have to manipulate your equation a little bit. You have F equals M times A. I want to solve for M, so I got to get it by itself. So on this one, we got to make sure we move A across, and we do that by division. So I'll help you a little bit with that one. So M equals F over A, and I'll let you run the calculations. Pause this video if you're working through those, because I'm going to give you the answers on the next slide, and I'll give you a couple more to practice after that. Here are your answers for those two questions. So your first one should be 3,200 newtons, and your second one should be 0.14 kilograms. Because it's a mass, I don't need a direction, because mass, I don't have direction for mass. It's simply a scalar quantity that only has a magnitude to it. I have two more practice questions for you to try. The first one being a sailboat and its crew have a combined mass of 655 kilograms. If a net force of 895 newtons is pushing the sailboat forward, what is the sailboat's acceleration? So this time we're solving for A, and then on the next one is the net force on the propeller of a 3.2 kilogram model airplane is 7 newtons. What is the acceleration of the model airplane? So again, you're solving for that acceleration. Pause this video if you want to try those, and when you're done, hit play and you'll get your answers to check and see if you did them correctly. So for the first one, we got if you take the force divided by the mass, you're gonna get 1.37 meters per second squared. On the second one, 7 divided by 3.2 gives you 2.2 meters per second squared. One last little bit. So we've done change force and acceleration. The last one, if we exert the same force on two different objects, or I guess if we change the mass of, or change the force on two different objects. So two objects, same mass. So if the mass of this car stays the same, we can look at the acceleration based on the force. So in this case, we have one person pushing, exerting this force, red on red's hard to see, and the car is going to accelerate in this direction at that magnitude. On this one, we have multiple people pushing, which notice a bigger arrow for force, a larger force in this direction, which means a greater acceleration here. So as mass stays the same, if force goes up, the acceleration also goes up. Force goes down, the acceleration also goes down. But that is today's lesson on Newton's second law. I would like you to take a minute and answer number 2 for me on this set. Provide 2 examples of Newton's second law in motion. And then I want you to explain how inertia and seatbelts go hand in hand. So answer those 2 questions, and then I will see you next time. Thank you very much for your time and attention. Enjoy the rest of your day.